Okay, hello and welcome to today's webinar. Good afternoon. My name is Arvind Krishnan, and together with my colleague Mike, we will be presenting this webinar to you. On behalf of EMWorks and all our staff here, we thank you all for joining with us today. Okay, we're going to start this webinar right now. If you have any questions, as I said before, feel free to use the chat window and type in your questions. And at the end of this webinar, we will be happy to answer them. Well, the topic for today's webinar is transformers and how you can derive equivalent circuit of a transformer using EM simulation inside EMS. The transformer equivalent circuit provides important information that determines the performance and the behavior of the transformer. For example, if you want to take this transformer and stick it into a larger system, okay? So you would need what is known as the equivalent circuit of your design. Now, EMWorks offers transformer designers with necessary tools to obtain accurate transformer characteristics that they can then use to simulate this transformer and also study its performance in the context of a very large system design. Okay. Now, transformer equivalent circuits are very standard. They may vary slightly depending on the size or type of the transformer as well as the type of the loading. But for most part, for most applications, the standard form that we will be presenting here will suffice for you to accurately model transformer behavior. Now, as I mentioned earlier, we're going to just briefly look at why we need a concept of an equivalent circuit. And this is widely used in the industry. The first thing is we would like to get a feel of what is the efficiency of the machine that we are designing. So that the equivalent circuit actually gives you a feel of that. Okay. And the second and a very important condition, which is unfortunately not very easy to test, is how would your transformer behave under different fault conditions. I mean, these are conditions that rarely or should never occur in real-time operation of your machine. But if you would like to understand how it's going to behave in case something wrong happens. And that's really where an equivalent circuit and together with the electromagnetic type simulation that we will be presenting here proves to be extremely useful. And finally, transformer is not an isolated machine. It's not just standing there and doing its thing. It's a part of a network. It's actually a part of a large system of many electrical machines that work together in harmony. And hence, engineers use different kind of system level simulation tools. Okay, and when you would like to do a system level simulation where a transformer is just a small part of your system, then you would require its equivalent circuit to perform a network system level type of simulation. So for all these above mentioned reasons, deriving an equivalent circuit of a transformer becomes extremely useful. And in today's webinar, we will be showing you how you can use SolidWorks and EMS product to actually derive the equivalent circuit of a transformer. Now, if one doesn't have access to these tools, so what would one do? I mean, transformers have obviously existed long before computers have become popular for engineers to do this kind of simulation. So, as most of you would be aware, one can actually obtain equivalent circuits without simulation. And the way to do that, unfortunately, is by actually creating the exact prototype of the transformer that you wish to design. For example, you would actually create a working model of a transformer. It could be called as a prototype. For all practical purposes, it will have a core, it will have both the primary windings and the secondary windings and so on. And then you would actually take it to a lab, and as you see in this small picture here, and you're going to do two kinds of tests. The first test is called the open circuit test, and the next test is called the short circuit test. We will actually be going over, actually my colleague Mike will be going over some of these in this presentation. Now, once you do these two kinds of tests in a real life lab, you're going to get some outputs that are useful in constructing an equivalent circuit of the transformer. Now, the idea of this webinar is to show you how you can actually circumvent this testing procedure to get to the equivalent circuit and actually get those perform those similar tests inside your computer while you if you're in the design stage of the transformer. Now we're going to talk about equivalent circuit elements, where my colleague Mike will take it over and explain to you about this slide. Over to you, Mike.
Thank you, Arvind. Can you just move to the next slide?
Yes, it is in the next slide. Just yeah,
okay. Thank you. Well, the equivalent circuits of a transformer, the most general one, the one we're going to talk about today, is quite simple. It consists out of two branches. It's a kind of a T equivalent circuit with horizontal and vertical branch. The horizontal branch is what is called the short circuit branch, or the serial branch, the one whose elements are obtained from the short circuit test. The other branch is called the magnetization or excitation branch, the vertical one, and its elements are calculated from the open circuit measurements. The short circuit impedance is basically the resistance of the winding in series with the reactance of the winding leakage. They are both obtained from that one short circuit test, and it's usually assumed that the primary and secondary resistance and primary and secondary reactance are the same. So whatever resistance or reactance you get in the short circuit test, you just divide that by 2, and you prescribe you prescribe the same impedance to primary and the secondary. In FEM, we actually have access to more accuracy, so our resistance and the reactance for the primary and secondary might not be the same, which is a benefit of higher accuracy coming from the FEM. The open circuit branch comes from the open circuit test. It has one resistor and one reactance in parallel to each other, and this is basically the everything you need to construct a basic equivalent circuit of a transformer. And just to clarify things, we are talking about transformer equivalent circuit with secondary elements referred to the primary, meaning we multiply whatever impedance we have on the secondary side by the number of turns, by the ratio of transformers squared. That's basically it. Arvind, you can pick up and move to the next slide.
Thank you, Mike. And then now we will just jump into what really happens when you do a simulation. Okay, and very shortly we will be showing you a demonstration of what we're talking about in the slide. So it will all be clear to you in a few minutes. Okay, now as my colleague Mike alluded, we're going to do 2 kinds of tests, which is called as the open circuit test and the short circuit test. But instead of doing them in a lab with a real transformer, we're going to do the similar tests inside our computer using EMS for SolidWorks as a simulation. And once we do those tests, we're going to extract these important parameters. And the real advantage of this is you can do a lot of prototype testing virtually with really no cost involved in doing these tests, you know, once you have the computer and the software. So ideally, this is a great tool if you're looking to optimize your existing designs or come up with the most optimal transformer design for your application. And by the way, the application does not need to be power engineering. there will be transformers. You can design all kinds of transformers using EMS. You can do planar transformers that are used in circuits inside PCBs and so on. So we're going to refer to a regular transformer here, but that is not limited to what is used for power applications. So we're going to talk about how EMS really plays a role in this equivalent circuit computation, and what are the key features inside the EMS software that enable you to simulate these transformers. First of all, you can do these two kinds of tests we have been talking about, open and short circuit tests. And you can do these things as studies that we're going to be showing you. Okay. Then let me go over other salient features inside EMS that actually acts as a very powerful software to for designing transformers. We have a material library that is quite exhaustive, and it's also editable material library. We have materials with core loss properties. We have materials with lamination information, and so on. So our material library, which is fully customizable, forms a very big part of doing these kinds of simulation. Okay. Next, we solve for resistances, inductances, and many things that that engineers are often interested in finding out from their designs. Okay. Also, one of the things that we need to take into consideration is the nonlinear behavior of the ferromagnetic materials. Okay. So the BH curve is not linear. It doesn't go as a straight line forever. At some point, actually, as soon as the value of H reaches a critical value, the BH curve, you know, the slope tends to fall drastically, and it's going to be almost parallel to the x-axis or the H axis here. So the nonlinear nature of BH curve is what a real life material is going to exhibit. And in EMS, we can actually simulate these kind of real life material properties. And finally, you can simulate these in a frequency domain, because each of these transformers are basically AC devices that have operating frequencies. So you can actually simulate these transformers at different frequencies and depending on your needs. So we do this in what we call as a frequency domain to do the solving, and by far it's very fast and efficient way of computing the equivalent circuit using simulation. Now we're going to talk about EMS model setter. What you will see is how do you set up open and short circuit simulation studies in EMS. How do you add lamination, score the loss curves for the core, etc. I'm going to walk you through all these in the demonstration. And finally, how do you obtain, what are the results that are needed to construct the equivalent circuit. So we're going to go over open circuit test setup, and over to you, Mike, if you can just walk us through the open circuit and the short circuit.
Thank you, Arvind. Thank you, Arvind. Sure. For the open circuit test, briefly, we make sure that the secondary winding is open, there is no current in it, and on the primary side, we supply it with a nominal with a current value, which primary side we supply with a nominal voltage, and we measure this small current which is carried in the primary winding. This kind of test leaves out, if you remember the equivalent circuit we've seen, that the secondary is now open. It doesn't play any part in the equivalent circuit. So what we're left with is basically the primary winding and the vertical magnetization branch. However, the voltage, because the current is so small in the open circuit test, we can basically always neglect the voltage drop on the primary winding. So, and if we do that, we are basically just left with the magnetization branch, which has one resistance and one inductance in parallel, which simplifies a lot the computation part. the measurements we make in this test are basically just the primary voltage and the current and the primary power. The primary power in the the primary power in the open circuit test gives us it's basically equivalent to the core losses, the hysteresis losses, the eddy current losses in the core iron. From that power and knowing the voltage and the current, we can easily compute by using these formulas the overall impedance of the magnetization branch, and eventually the impedance of each component, or the resistance or the reactance of each component that form the parallel branch. The short circuit test is kind of set up in a reverse way to the open circuit test. We keep the secondary winding short circuited. We make sure that the voltage on the secondary is 0, and then we supply the primary with a nominal with a small voltage which will produce the nominal current. We again measure the voltage and current on the primary and the power, but this time the power gives us the value of the copper losses. From these three measurements, we can easily compute first the overall impedance of the winding, and eventually the resistance and the inductance. This inductance is the inductance of the leakage, inductance. Again, we can assume in reality, when these tests are performed, engineers assume that resistance and reactance of the primary and secondary are the same, so they just divide the results by 2. But in EMS, we can actually get the accurate results for both windings. Okay, you can take on.
Thank you, Mike. Now we will go through the actual demonstration, where I'm going to be opening up SolidWorks, and I'm going to be showing you how to perform these open and closed circuit tests inside EMS, and then we will transfer all the results that we obtain to Mike, who will just construct the equivalent circuit for this transformer. So with this, without any further ado, I'm going to just transfer the screen to SolidWorks and see how simulation is performed in EMS. Now, what I have here is a transformer that is designed using SolidWorks. I have a core, as you see here. I can actually take a section so it's clear. I have 2 sets of coils. One is the primary coil, and the other is the secondary coil. You know, they're just outer and inner. And you can see this is the model that is created of a transformer. This is a single phase transformer, but it really doesn't matter. You can simulate multiple phase transformers, 2 or 3 phases in a similar manner. The idea is to be able to create the solid geometry using SolidWorks, and then you will be able to do a simulation. Okay, now as you see here, there is an EMS tab here. EMS is an add-in product to SolidWorks. So if you're designing using SolidWorks, EMS is an add-in product that you can add into your SolidWorks and use it to do simulation. In addition to SolidWorks, EMS also works with Autodesk Inventor and SpaceClaim. So the same simulation that I'm showing you right now can actually be done inside Autodesk Inventor as well as SpaceClaim. But for this demonstration, we will stick to SolidWorks. Okay, to do a simulation inside SolidWorks, we have to go to the EM tab, the EMS manager, and the first step that one needs to do is to create what is called as a study. So let me walk over some of the steps that are needed to set up a problem. So the first thing that we do is create a study. When you create a study, there are several different analysis types available inside EMS. Now, because today we are interested in transformers, which are basically AC machines. We're going to just subject ourselves to AC magnetic type of simulation. Okay. Now, once you have selected the type of simulation, now here is where you would input your frequency. So usually the machine that we are trying to analyze works at 60 Hertz. So you can go ahead and put in the frequency. But I do want to let you know that EMS is capable of simulating transformers that work under several hundred kilohertz. So basically, even if you have transformers all the way from 50 Hertz to several hundred kilohertz, this is just one product that allows you to do all these kinds of simulation. Okay. There are very many things that I will not be going through. For example, a topic for another webinar is to understand what each type of solver does for EMS. Now, right now, this AC magnetic is the solver that we will use to analyze transformers. This is if you have AC signals. Now, you might ask what happens if I have a different kind of signal. Maybe I have a pulse signal that is periodic. Maybe I have a DC signal, etc. EMS has several studies to take care of them. For example, magnetostatic, if you have just permanent magnets or DC current, we can use magnetostatic. Or by far the most comprehensive is the transient magnetic, where you can have any kind of signal as a function of time that you, including periodic signals that can be analyzed. Okay. Now let me quickly go over a few additional coupling multiphysics functions that EMS can provide. For example, you can couple electromagnetic simulation to thermal, and for that you can resort to thermal coupling. Or if you're designing solenoids or motors, etc., where you would like to couple it to a moving, some kind of a moving kinematics and dynamic motion study, you can do coupling to motion. Okay, these are some of the options available for you. Now, once you create a study, you're going to create a study. It's going to create what is known as a study tree, as you see here. Okay. Now, the next step in defining the study is to define the materials in your design, in your simulation. Okay, there is one part that I've hidden that I'm going to show you is the concept of air. Okay, now air is extremely important for electromagnetic simulation because the magnetic fields and the electric fields, they are not only present in the magnetic substance and conductors, but also in the air region in and around it. Okay, so to be able to capture this, one needs to include air. Okay, it's very easy to create air as a solid geometry in any of the CAD systems, and you can use that for simulation. Now, once you create the air, you can apply materials. EMS allows you to apply materials using a database that is readily available inside EMS. Now, this material library is fully customizable, and one can actually use some of the materials that are available in our library, or you can create your own materials and use that for simulation. Okay. Today I'm just going to be going over especially the material with respect to the core. Okay, so we apply air to the air geometry outside. The two coils are applied a conductor material like copper, and then let's just divert our attention to the core material. Now, here is a core material. That's basically an M27 type of ferromagnetic material. It's laminated. The lamination thickness is about 0.36 millimeters, and the core material actually has a core loss curve that is also as a part of our standard database. So if you have a material that is different, if you have the core loss curves, if you have the BH curves, by all means you can input them inside EMS and use that for simulation. So we assume for the core loss, this core for most part is made of laminated steels. We have to specify the density, the lamination thickness, and the stacking factor. And once you specify these things, EMS will automatically incorporate the effects of lamination in your simulation. So once you apply the core material, with that, our material application of materials is completed. Just to recap, you can apply materials in EMS using our standard material library, or you can create your own materials and use it for simulation. Now, next we're going to do these two. Let me go ahead and hide the air geometry. And we're going to focus next on these two open circuit as well as short circuit tests. Really, as Mike mentioned earlier, we apply some kind of an excitation to the primary circuit. Now, the primary coil is connected to 110 volt RMS supply. So we select the components where we want to apply this voltage. We select the cross-sectional phase. As you see here, it's highlighted in blue. This is the phase through which the current is injected. So this is really a cross-sectional area through which your copper conductors are going to carry the current. Okay. Now this primary coil is made up of several different conductors, actually 100 turns to be precise, and it's made up of wire gauge 9, AWG 9 wires is wound for the primary. Okay, and the voltage is 110 volt RMS. Now next this is an open circuit test, so needless to say, in the secondary we follow a similar procedure where we select the components that define the secondary circuit, the secondary coil. We select the normal phase through which the current is gone, but the only difference here is obviously there is it's a wire gauge, it's a different thickness wire that is wound, and you have less number of turns. Because it is open circuit, you're actually not there is no current in the secondary, so you're going to apply zero current in the secondary. So this is how you would actually set up an open circuit test in EMS. Now once you do that, you are now ready to go ahead and analyze the problem and look at the solutions. Okay. Before we look at this solution, let me just quickly go over what we did in a short circuit test. We created another study called a short circuit test. We have defined the materials as per we did similar to the open circuit test. Now, in a short circuit test, we're going to define a voltage to the primary. It's certainly not going to be 110 volts. It's going to be a fraction of it, maybe 5, maybe 10. In this time, we can start with 10 volts. The number of turns and the coil diameter, etc., remain the same, but we're going to start with 10 volts. Now, really, this is where the convenience of EMS comes into play. In a lab type environment, you're going to try and guess this voltage. You're going to raise that slowly from, say, 0 volt, and you're going to keep raising till you see some nominal current in the secondary. Okay. We can do a similar setup here. You don't have to guess 10 volts. You can start with 1 volt, 2 volt, 3 volts. In fact, EMS allows you to parameterize this. You can actually set up this voltage as a parameter and ask it to vary it and get a response of different currents based on the voltage. Now we found out the most optimal voltage for this particular transformer is around 10 volts. So we applied a 10 volt RMS value to the primary. Now the secondary is short circuited. Now what that really means is we apply a 0 voltage in the secondary. So it's actually shorted. So which means there's going to be a spike in the current, but to eliminate that, we're going to keep the primary voltage as low as possible. Hence this 10 volt. Okay. Now this is really the setup as far as the open and short circuit test goes. Now we are going to go and look at some of the results that EMS gives you in the open circuit test. Now I'm going to start with some qualitative results. What I mean by qualitative results is this allows engineers to look at the flux. What is the flux value inside your core? What's the maximum flux value, etc. And then we will get to particular quantitative results that are useful for constructing an equivalent circuit. Now let's look at the magnetic flux density. Now I'm going to take a section plot of the magnetic flux density. Now this is the distribution of the magnetic flux inside my model, inside my core, for example. As you can see here, the maximum magnetic flux density is close to 1 Tesla, which is a much lesser than the saturation point of steel, which is close to 1.5, 1.6 Tesla. So you want to be operating in this region where you don't saturate the steel, but at the same time you operate at around 60 to 80% of saturation. And now by getting a qualitative feel of what is going on, engineers actually have a better appreciation for what it is. Certainly this is something that is almost impossible to achieve in a laboratory type setup, where you can find out the magnetic flux density at almost every point inside your model. I think is something that is not achievable, and hence these qualitative results that EMS produces becomes very useful and effective. We can visualize the same thing in many different ways. You can look at the flux as vectors, because these are really vectors, and you can look at it as a vector plots, as you see here, how the flux density is moving inside the core as a vector. So this is possible to visualize. You can zoom in and zoom out and look at these values very closely. Okay. Now we are now ready to take a look at the result table. Now this is really where the most important parameters that are required for open and short circuit tests are conveyed. Okay. For example, I'm going to go over a lot of these tabs in the result table. One can obtain the inductance value for your coils, the primary coil and the secondary coil, both the self as well as the mutual inductance. EMS gives you those results. You can look at the flux linkage, you can look at the impedance matrix, you can look at the leakage inductance. And this is one of the important things that Mike mentioned earlier, is important in the case of an equivalent circuit. So the primary and the secondary leakage inductance are some things that EMS gives you as output. Okay. In addition to it, it's very important to understand what is the current in the primary for an open circuit test. Now, the current in the secondary is going to be 0 in an open circuit test because we set it up that way. And the primary current is given here, both the real and the imaginary part. So it's close to around 0.26 amps is really the resultant current that goes into the primary circuit. Then we also have the next important parameter that I'm going to just quickly jump to is the core loss. Okay. Now it's very important. The open circuit test is designed to compute the core loss of your core or of your transformer. Okay. Now this core loss is now 11 watts, 11.058 watts, and look how easy it is really as a feedback. You run a simulation and you're going to actually get the core loss in your core. So if you and this kind of tells you really how good your core is and how good your material is and so on. So this is important. In addition to the core loss, one can get the resistance values. Okay, so the primary and secondary, they are all made up of a number of turns, and one can straight away read the resistance of the primary coil as well as the secondary coil in EMS. Now these are some of the values that are important for constructing an equivalent circuit, and we give you those values automatically in EMS. Now let us quickly go to the short circuit test, and we did a similar short circuit test, and we are going to take a look at the result table here. Okay. Now this is the inductance matrix. What is important in the short circuit test is really the resistance values and the winding losses. So if you look at the winding losses, we can compute the winding losses that comes as a result of the short circuit test. The resistance values that are computed by the program is really the DC resistance. What you see here is the DC resistance. We also compute the impedance in the open circuit test, as you saw. So you can get both the impedance as well as the resistance, both the inductive component as well as the resistive component. We do get. So with this, pretty much it gives you a good idea of how you can do a simulation of your transformer inside EMS. Now I'm going to hand over the results that we got now to Mike, and Mike will take you through how to complete the equivalence.
Thank you, Arvind. One of the interesting things about getting this equivalent circuit done was that it almost took more time to compute the final results for the equivalent circuit from the parameters from the EMS than to run the EMS simulation, because the results from the EMS simulation were complex numbers, and the calculation involved dealing with complex numbers. It almost took more time to do these few formulas than to run simulation in EMS, which is really fascinating and tells you how quickly and how effectively you can get your results. You can perform your simulations inside EMS. The equivalent circuit we have here, basically one of the first things that I've noticed after we completed the circuit was how closely impedances on the primary and on the secondary match one another, and it really justified. It really showed me that the assumption engineers usually make, that that primary and secondary have exactly the same impedance, is kind of justified. However, it's still nice. It's still nice to have the full accuracy that you can get through using EMS. By looking at all these elements and their values, you can get a lot of information about your transformer design and where you are with the particular version you are simulating. What do you need to do to change some performance parameters? What do you need to do to increase losses, to decrease losses in the copper, or to reduce the short circuit current? Basically, the resistances in the series branch tell you about the copper losses. The reactances in the series branch will tell you how much of the flux are you actually losing, how significant the leakage is. And if you go back to the EMS and SolidWorks, you can and you look at the field plot, and you can actually visualize the leakage and find a way to reduce it and to get this parameter in the equivalent circuit smaller. In the parallel branch, you have this the resistance and reactance in parallel. The value of this resistance kind of indicates what is your loss in the core, and what is the amount of heat you're going to be releasing in your iron, and what you can see where you are, and whether you need to reduce it, or you're fine where you are. The same thing for the reactance. By looking at its value, you will kind of know how what magnitude of the magnetization flux you're able to achieve in your core. Again, if you find that either one of these values is excessive or not large enough, you can go back to SolidWorks. You can tweak a dimension or two, rerun the simulation, reconstruct the equivalent circuit, and see where you are. Again, you got to keep in mind that all these variables are interconnected, and changing one will definitely have some effect on the rest of them. And the best way, the best environment to capture this relationship between all these elements, between all these variables, is SolidWorks with its and EMS with their ability to easily change parameters and to get results within a matter of seconds. Arvind, you can take on.
Thank you, Mike. So I hope we showed you enough things to get you excited about what you can do with EMS in terms of your transformer simulation. So let me quickly recap. Okay. So what we saw today is how do you extract equivalent circuit of a transformer without ever needing to go to a lab. All you need is the design of your transformer, your core geometry, your coils, and you can actually do that using EMS. Okay. So the simulations, both the open circuit as well as the short circuit tests, can actually get you all the parameters required to create an equivalent circuit, and Mike did a good job of creating one for the transformer we had. Okay. The advantage is of these is obviously to reduce the prototype, that number of prototypes you need for testing, and helps you to optimize your design. Well, now there will be obviously a lot of questions related to what more can I do here, and due to the lack of time, we certainly skipped some of the more interesting and important things that could arise from that. On a future webinar, we certainly were going to look at a coupled thermal simulation. Is really to understand, okay, I got my equivalent circuit, but I also know my transformers are going to heat up. How much is this heating, and why is it getting heated, and how much is it getting heated? What is the maximum temperature reach? What are the hot spots? All of this can actually be done inside EMS. Actually, you could do it yourself. And in the next slide, I'm going to be showing you how you can actually get EMS and try it out for for a couple of weeks. So you can actually do that. Not only that, we added a new feature to compute the thermal stresses as well in the latest release of EMS. So in addition to getting the temperature, you can also get the stresses involved due to this temperature. So you can do both thermal and thermal stress calculation. I will obviously cover these as a part of future webinars. Okay, so with that, I'm going to thank you all for patiently hearing out Mike and myself in this particular webinar. I would like to divert your attention towards our website, emworks.com. You will be able to get white papers, customer testimonials, etc. At our website, emworks.com. And even more important is the ability to get a free trial. And I think this is really where you're going to see the power of EMS for yourself. So if you go into our website, emworks.com, I actually happen to have them on my screen right now. You're gonna take a look at these things in the homepage. If you're ready for a trial, you can click for ready for a trial. All we need is to get an email address from you so that we can send your the trial license. The product that we looked at today is EMS, so you can select that. There are obviously other products in our portfolio, and that's something that I would like you to explore using our website. We promise you that within 24 hours we will get back to you and offer a full free trial of a full functional product. Okay, so whatever I showed you today can actually be done using your own computer by yourself in this one. Okay. Also, I would also like to divert your attention towards our YouTube channels. If you haven't already looked into our YouTube channel, there are actually several dozen videos that talk about different aspects of EMS. There are videos that help you to learn the product. There are videos that help you to understand several different applications. There are also prior webinar videos. So please take a look at it when you have time, and you can always write to us or call us, and we'll be happy to answer your specific questions. With that, we thank you all, and now I'm going to open the floor towards some of the questions that that we got here, and let me see if I can answer some of these questions here. Okay, okay, the first question is asked by a gentleman, and it reads as follows: could you alternatively perform an electrostatic simulation of the transformer windings in order to determine the capacitance and inductance for input into an equivalent circuit? Yeah, you can certainly perform a magnetostatic simulation to get the equivalent yeah, capacitance and inductance, yes, that is certainly possible. But the electrostatic simulation is actually of another interest as far as transformer design is concerned, is that is really when you want to understand if there is going to be any arcing, or if the electric field is going to break down anywhere close to your transformer. So this is also kind of important, because you're going to have some kind of an insulator that separates the windings from your core, and you would like to understand the electric field in that region. So you can actually do an electrostatic simulation to understand the electric field distribution, and you can see if any potential breakdown could occur. Okay, you could do that. The next question is the value of what is the value of the DC of the resistance that we give out in EMS. Now, for the most part, in the in what you saw, the value is the DC resistance. There are ways of computing AC resistance in EMS, and we will probably take that up in another topic. It's basically depends on the type of coil that you created, because we created what is known as a wound coil, and here we assume that there is hardly any skin effect in the coil, or eddy currents or induced currents in the coil. So for the most part, we compute what is called as just the DC resistance. But EMS is capable of computing AC resistance. You just have to define another type of coil, which is called as a solid coil, and we have the ability to compute the AC resistance as well. This is again with regards to thermal simulation. If you go to our YouTube channel, I think there are a few videos that talk about our thermal capability. You should be able to get them. Otherwise, we'll probably cover them in a future webinar for sure.
Arvind, I would like to answer to the next question. The one asking, is it possible to see matrix of inductances and series capacitances of winding, and to see how does the overvoltage affect the electric in different zones of the winding. This is certainly possible to perform in EMS. The only thing that needs to be done is to define geometry and of different sections of the winding separately, and to treat them as a solid coil. The same thing you talked about for the AC resistance. So as long as you have the accurate geometry of the winding, and you have accurately defined the material, the spacing between the turns, there should be no problem of computing these inductances and capacitances that you want to use to simulate over voltages and voltage surges due to different transient effects.
There's another question which talks about, are there any limits in the number of windings to simulate? That's a very good question. See, if you are doing a wound coil as we did now, there is really no limit to the number of turns. But if you want to design each and every winding, obviously your computer resources are going to be coming into play. So it all depends on the kind of memory and the kind of computers you have. We don't put in any limits to the number of windings that you can simulate, but technically, if you have several hundred turns or even 100 turns as what we had in this one, and if you want to draw out each of these wires, I think it is quite an arduous task, and that itself becomes a simulation by itself to really understand how the different winding wires interact with one another. So there is no real limit, but that limit is brought out by the hardware that you have. And in general, that we are looking at a little bit more higher level as far as the transformers go. So we kind of assume, in this simulation at least, we assumed that it's a wound coil and it's perfectly wounded, and there is really going to be no problem as far as what's going on between the windings. But if your main topic of interest is to really understand what's going on between the windings, it might require a different kind of geometry and a different kind of simulation. And
Yes,
Mike, if you would like to add.
but there is probably no better place to create random geometries than SolidWorks, and technically, as you've said, there is no any limits to the number of windings that you can simulate. Depends, as long as you have reasonably powered machine, you can perform any kind of simulation of that kind you wish. And the next question says, by the same gentleman, is it possible to simulate forces due to short circuits in single phase or three phase and determine strengths? Yes, of course. There is a feature called force calculator in EMS. You just prescribe that feature to the domain where you want to determine the forces acting on it. In this case, your winding probably. You will have to probably use the different type of study, the transient study. In it, you apply any kind of current profile that you see fit, and EMS will easily compute the forces on your winding.
Okay. Thank you, Mike. And I think with this, we will end this webinar. And on behalf of EMS, EMWorks, I thank you all for attending today's webinar. And have a nice day. And we will see you in a future webinar.
Arvin.
Yeah.
There's two questions about the AC, DC resistance, and one about the thermal.
It's all answered, Dad.
Okay.
All right. Thank you very much. Have a nice day. Bye-bye.
Thank you all.